This is lecture 4 on your engineering mechanics. So today we are going to discuss these topics, that is the equilibrium law and law of superposition and its corollary theorem of transmissibility. Then we will discuss about action, reaction and free body diagram. So yesterday, I think if you recall, we discussed about the parallelogram law and how to solve it analytically. Okay. Now today we will start with the equilibrium law. So law of equilibrium, we have discussed that, if you remember, that if two forces are to be in equilibrium, the two forces needs to be meeting three conditions. One is magnitude wise they should be equal, so equal in magnitude, then opposite in direction, collinear in action. So these are the three conditions the two forces should have if they have to be in equilibrium. Okay. Now we will discuss the next topic, that is the law of superposition. So what is law of superposition? It is a law, therefore it is only found to be working. So it is not, so far it is not disproved, it is proved by experiments, not theoretically by using other means. So the law of superposition, before giving the statement, let me tell you what is law of superposition. If I have a body on which there is a system of force which is acting, for example F2, F3, F4, F5, like that. Already a system of forces are acting and it has some effect. Maybe this system of forces keep this body in equilibrium. Now it may be in equilibrium or may not be in equilibrium. If the resultants of these net forces are zero, it will be in equilibrium. For example, you say it is in equilibrium. Now if I introduce another system of forces, for example, I introduce a system of force which is say F6 and F7. So F6 and F7 is another system of force I am introducing. The nature of the system of force I have introduced is such that they are already in equilibrium. These two forces are in equilibrium. Okay. So if I introduce such a system of force, this is not going to have any effect or any change in the effect of the original system of forces. So this law gives me the freedom or authority to introduce a system of forces which is already in equilibrium on my own wish. without affecting the original effect of the system of forces. Okay, so like this I can introduce another system of forces which are in equilibrium. For example, there may be three forces in equilibrium: F8, F9 and F10. These three forces are already in equilibrium. I can introduce that forces without changing the net effect of the original system of forces. So law of superposition says that I can introduce a system of forces which is in equilibrium without changing the original effect. It also gives me the authority to remove it. It not necessarily that about introducing, you can also remove a system of forces in equilibrium without affecting it. Okay, so this is the essence of the law of superposition. The statement is that the action of a given system of forces on a rigid body in no way be changed if we add or subtract from them another system of forces in equilibrium. So this is a statement. So you can either add or subtract another system of forces in equilibrium. That will not change the original effect. Okay, this is called the law of superposition. You have any doubt? Okay, now we'll take an example how that could be used. So I am going to use this law to prove the theorem of transmissibility. Theorem of transmissibility. What is the theorem of transmissibility? A force acting on a rigid body can be moved along its line of action. The point of application of a force may be transmitted along its line of action without changing the effect of the force on any rigid body on which it is applied. This statement is called the theorem of transmissibility. So theorem of transmissibility states that on a rigid body, if a force is applied, say that is P, its point of application can be moved along its line of action. That means it can be moved along its line of action. That tells us that it can be a sliding vector. Okay, this force on a rigid body, as per the statics is concerned, it can be moved along its without changing the effect. Whatever be the line point of application is A, this can be shifted to B without its changing its effect. So it is called transmissibility or theorem of transmissibility. As a statement says, a theorem can be proved. Okay, law cannot be proved by some other basic additional fundamental things. Okay, it can be experimentally proved, but a theorem can be proved by some other law or some other further things. So I am going to use a law of superposition to prove the theorem of transmissibility. So let me introduce, using the theorem of law of superposition, I am going to introduce a system of forces which are in equilibrium. For example, here that is P dash and P double dash. I'm introducing this, a system of forces in equilibrium. The forces are P dash and P double dash. They are equal in magnitude, opposite in direction and collinear action, therefore they are in equilibrium. I can introduce like that, but I have chosen such that the line of action of these forces are aligning with the line of action of this force P. For convenience I have taken, but as per the law of superposition I can introduce the P and P dash anywhere, it's not going to affect P dash and P double dash, which is an equilibrium. I can introduce in any orientation and any point of application, doesn't matter. It will not going to change the effect of the force P on this rigid body, but for convenience to prove the theorem of transmissibility I have introduced this. Okay, so now if you look at this, who has given you the authority to introduce this? Then I will say law of superposition has given me the authority to introduce the system of forces in equilibrium. Fine. Now what I am going to do is I am going to use the same law of superposition to remove two forces which are in equilibrium. What are the forces I am going to remove? P and P dash. You look at P and P dash. What is the nature of P and P dash? They are equal in magnitude, opposite in direction, collinear action. Therefore, P and P dash are in equilibrium. Therefore, the law of superposition not only gives me to the authority to introduce or add, it can also gives me the authority to remove. So using the same law of superposition, I remove the two forces are in equilibrium, that is P and P dash. Now what I end up is, I have a force P double dash which has a magnitude of P, it has the direction of the original force P, but only thing is now the point of application is shifted to B. From A it has been shifted to B. So using this I prove that you can execute this in anywhere to show that the point of application of force can be moved. Okay, so that is the theorem of the theorem of transmissibility says that the point of application of force can be moved along its line of action without changing its effect on a rigid body. So that I have proved it. How I have proved it? I use the law of superposition. So theorems can be proved like this. Okay, you have any doubt? So this is one law of superposition is one powerful tool. You will see that we are going to use it in number of places. So now about the theorem of transmissibility, whether we can use it in all domains of engineering mechanics or all domains of mechanics, whether it has any limitations, whether you should be cautious about using this theorem of transmissibility. So for that we will take one example. We take say a rigid body, say identical rigid bodies. You can think of identical rigid bodies and say there is a force P is acting on it like this. Then you say in the another body which is identical, there is a force Q is acting on it, and these two bodies are in equilibrium. That means the forces, they are in equilibrium means the two forces P are equal in magnitude, opposite in direction, and collinear in action. Q is also like this. But you have seen that even though they are in equilibrium, the internal forces are different. In one case it is tension, in other case it is compression. Now using the theorem of transmissibility, so this is a member which is in tension, this is a member in compression. According to the strength of material, the internal stresses that they are subjected to is quite different. But now I am empowered with the theorem of transmissibility, which says that the point of application of the force can be transmitted along its line of action. So if I say this is point of application A, this is point of application B, I can move this, transmit this along this here. What will happen? So if I say this is P and one is P dash to distinguish it. So I can take this slide this along and bring it here. What will happen is this will become P dash, but its direction is like this. I bring that P here to this point A, then the direction of P is like this. So using the theorem of transmissibility, if I transmit the point of application of the force P and P dash, their point of application I say in this case is reversed, it will be still in equilibrium. As per statics is concerned, it will be still in equilibrium. There won't be any change at all, because statics deals with the equilibrium of bodies acted upon by forces. That as per statics is concerned, there is no issue. But when it comes to the internal forces, what happens? Can you think of this is still in tension? No, it is in compression. So if I use the theorem of transmissibility, I have to see that whether I am bothered about the internal forces. If I arbitrarily use this, then in problems involving the internal forces, this may not work. Even the other worst case is like I transmit this to a point C here somewhere, then you will see that P dash is shifted here, P is shifted here, so no longer they are here. Now you see what is the kind of stresses which are, this will be still in equilibrium. Statics is satisfied, this is in equilibrium, but when these two forces are acting at a point, what kind of stresses this member will be subjected to? No internal force, internal stresses will not be there. So you see that the theorem of transmissibility has the limitations. What are the limitations? When these problems involving, when you are concerned about the internal stress situation also, you cannot use this arbitrarily. For statics is no problem. When it comes to the problems in strength of materials or problems involving this thing, you have to be cautious. You don't say that I use a theorem of transmissibility, I just transmit it. Okay, so that is one limitation that you have to take care of it. You have any doubt? So we discussed about what is theorem of transmissibility. We proved that theorem of transmissibility using the law of superposition, and also we have said the limitation of using the theorem of transmissibility. Theorem of transmissibility cannot be used where you are concerned about the internal stresses or the internal forces, so therefore you have to be cautious. Okay, as per statics is concerned, theorem of transmissibility can be used without any botheration, because the system will be still in equilibrium, no issue about it. But when it comes to the strength of materials or other subjects which where internal stresses you are bothered about, you cannot use it. That is the limitation. Now we'll take another example. We have a rigid body. We have a force acting at point A. We have another force acting at point B. How to get the resultant of these two forces? How to get the resultant of these two forces? Yeah? You remember, you can use the parallelogram law. Parallelogram law is stated for the two forces acting on at the same point. The point of application of both the forces must be same. Okay? The two forces acting at a point A, then the resultant can be obtained by constructing a parallelogram, the diagonal of the parallelogram with the resultant. But here what happens is that they are not acting at the same point. They are acting at the two different points. So how to get the resultant? Yeah? Yeah, now you can use the theorem of transmissibility. If you use the theorem of transmissibility, it can be transmitted along the line of action. You can also transmit this here, let it intersect at a point C. So using the theorem of transmissibility, you can move this here and here so that they can act at the intersection point C. Now both the forces are going to act at the same point, and you shift these two forces P and Q using the theorem of transmissibility. Now you can use the law of parallelogram law to get the resultant forces. Okay, so theorem of transmissibility addresses the problem of getting the resultant of two forces which are not acting at the same point. Okay, so suppose their intersection is not on the body. Suppose I have a situation where you see I have a force P and force P acting at a point A. So its line of action is like this, and I have another force Q which is acting at a point B. So if I extend it here, their intersection is going to be away from the body. It's not on the body. So still what you can think is this body is extended imaginarily. You can imagine that this body is extended, it contains this point C, then you can shift it there and get the resultant. Okay, so that's how you can get the resultant of two forces which are not acting at the same point. Now we have another situation. Specifically, we can use the theorem of transmissibility to our advantage. Let us take point A. There is a force P is acting. There is a point B in which another force is acting, which is nearly parallel Now P and Q are nearly parallel. Not exactly parallel. If it is parallel, we don't have a solution. If they are nearly parallel, okay, very small differences there. So they are nearly parallel. How do you get the resultant? So there still you can say that nearly parallel thing, you can extend it here, extend it further. They may intersect nearly at infinity. Okay, so if you think of a situation like that, I have said that in the earlier case you can extend it and think of it as intersecting at a point which is not physically located in the body and still work. But in this case you see it is going to be somewhere far away. When you say nearly parallel, it may intersect at nearly infinity. So that is going to be an ugly or not an elegant situation to say that you imagine this point C is somewhere here and then I get a resultant. No, it's going to be difficult. So in that case I can use the law of superposition to solve this problem. So what I do is I can introduce a system of forces in equilibrium. Say for example, I'll take force S and S dash. S and S dash are the two forces which are in equilibrium. They are equal, opposite in magnitude and collinear in action. I can introduce that here into the rigid body without changing the original effect of P and Q on that rigid body. Now you can, these two forces is there. Now you try to find the resultant of P and S by constructing a parallelogram. So you will have a new resultant coming up here. I call it as P dash. The resultant of these two, I can call this as say this is Q dash. Now they are not nearly parallel, they have now an angle, acute angle. So if you extend their P dash and Q dash here, so technically speaking, once I draw this P dash and Q dash, technically I can remove these forces which are the components. Once a resultant is found, you can remove this. They are no longer existing. So the components can be removed and from the system. Okay, so you have now P dash and Q dash, they intersect at a point now C. Now that is going to be the new point of application. Use the parallelogram law and find out the resultant. Okay, so this will not work if they are exactly parallel, because when it is exactly parallel, P dash and Q dash also will be turned by the same angle, then it will still remain to be parallel. So dealing with such cases comes into the chapter of parallel forces. Okay, when it is nearly parallel, we can use this technique. There you can see again, logically we are using the law of superposition. Okay, so wherever you do it, you have to say that I am using according to the law of superposition, I do this. Okay, any doubt? Now we'll go to the next topic. So next topic is about the constraints. Okay? What is a constraint? You can say you know the literal meaning of constraint. That is a restriction. Okay? So restrictions to the free motion of a body in any direction is called constraint. Restriction to free motion of a body is called constraint. Okay, let me take it, write it. Any direction is called constraint. Now we have to discuss about what is the free motion, what are the possible free motions of a body. So if I take a body which is in space, then what are the possible motions a body can execute in space? If you think of, following a conventions, you can always construct Cartesian coordinate system consisting of x, y and z axis. Then if that is the case, this body can translate along x axis, it can translate along the y axis, it can translate along the z axis. So three possible translations. And also it can rotate about x axis, it can rotate about y axis, it can rotate about z axis. That means three possible rotations. So any body, unconstrained body, that is it has a free will to move anywhere it like to do, then it has 6 degrees of freedom. So a spaceship will have 6 degrees of freedom, so it can have 3 translations and 3 rotations. That is about the Cartesian coordinates x, y and z. So if you are constraining the body is on a plane. Okay, if it is on a plane, then you can think of a Cartesian coordinate system again, but one axis will be missing. You can say x and y. The body can translate along x axis, it can translate along y axis. That means it can have a x axis, y axis. Suppose it goes like this, then it has executed a translation along x and y. Okay, then it can also rotate about its axis. So it has 3 degrees of freedom. So if you are not allowing a body to move, then that is a restriction to the free motion of in any direction is called a constraint. Okay, so what is the kind of motion a person can execute by walking? So I am walking on this stadium or this the platform. What kind of motion? What are the ways that I can possibly move? So I can think of x, y and z directions. So in x direction I can translate, okay, in y direction I can translate, and I can rotate about the z axis. I would not like to go like this or another axis. So what kind of motion a person can execute on a plane is only x, y and z axis. X, y plane motion and a rotation about its axis. I cannot be rotating another 2 axes, or I cannot go down, or I cannot go either up or down. Okay, so the floor or the ground is a restriction. It is not allowing to move on the vertical direction. It's not also restricts somehow, it restricts the rotation about this axis. So this anything which restricts is called a constraint. So if you in statics, if you think of a body, say for example a ball which is on a floor, a ball is on a floor, obviously cannot move downwards. So the freedom of the body to move downwards is restricted. So the floor is a constraint in the vertical direction, especially going down. Okay. Similarly, if I take the ball, the same ball, I use a string to, I think this will be confusing. Okay. Here, if I take a ball and hang it as a pendulum, still the ball is restricted to move in the vertical direction. So here the constraint is the string, whereas for this ball the constraint is the floor. There can be multiple constraints. You need not think that constraint will be only one. So it can be multiple, plurality of constraints is possible. So you can think of another ball restricted like this. This is a wall, vertical wall. It's like a pendulum, but it is a pendulum, it's not allowed to go to the equilibrium position. The wall is preventing it. So here you have a constraint on the ball. Ball is not permitted to move downwards because of the string. The ball is not permitted to move on the horizontal direction, especially in one direction, because of the wall. Okay. So in statics problem, you have to identify the constraints which are involved. Then you also have to find out the interaction between the constraint and the body. So that requires certain kind of a prior knowledge or understanding of the type of constraint. Now, what kind of interaction that will happen between the two? Okay, so that is what is defined by the Newton's third law, which is called action and reaction. Okay, so if it is a constraint, the constraint is the floor, there is a kind of a force interaction. So the ball is having a weight W acting through its CG, and this if you consider that this is the contact is assumed to be a point, it is a spherical ball. If you assume it to be a point, then you will have a reaction coming from the floor. And what is the direction, and what is the magnitude, what is the point of application of the reaction R? Since the W is acting and it is contact, this will be vertical in direction. So that weight W will be acting upon the constraint. The floor will experience the weight. The floor will experience the weight of the ball. What will be the reaction? Reaction will be, as per Newton's third law, it will be action and reaction will be equal and opposite. Okay, so the reaction from the floor will be equal to the W. So this also will be equal to the W. And since the system is in equilibrium, we can say that these two forces, the reaction acting on this and the weight, action force weight, and the reaction will be collinear. Okay, so I have a constraint, the constraint is applying a reaction R. So the action reaction will be equal. This is Newton's third law. It may look obvious because you used it several times, but if somebody asks you that how can you say that the constraint is giving exactly the same force, then it is not you have found out, it is according to the law of Newton's third law, that action and reaction will be equal. Now about this constraint here in this problem, the weight is acting downwards, this also to be vertical, the string is being pulled downwards with the weight, so the string will apply a reaction of R upwards, that will be equal to W. And these two forces, under the action of these two forces, we find that this ball is going to be in equilibrium, so this force is W and this thing has to be equal, opposite and collinear in action. Now about this situation, you have the weight which is acting downwards. This ball is touching the string cannot be loose, it has to be under tension. So this ball is touching the string will offer a opposite force. Okay, so the force from this will be like this. I can say that tension is S. What about the reaction from the wall and this ball? There it is touching here at a point. There you have to be little careful. What kind of the interaction that will occur is, if this wall is assumed to be smooth, okay, if it is a smooth wall, meaning that it is frictionless, so if a constraint is frictionless, then the reaction will come only in the perpendicular direction. So if I say this is my wall, the reaction will be perpendicular to it. If it has a friction, it will not be perpendicular. What is the angle that we will learn when we are learning the chapter on friction. So if you assume this wall is a frictionless wall, smooth wall, then the reaction will be acting perpendicular to the surface. Okay, if it is a curved wall, still you have to find out that the point of contact, the normal direction you will have the reaction which is coming out. Okay, so the constraint here, in this case it is the floor, here it is the string, here you have a wall and the string. You will see that these constraints are not permitting this to freely move. At the same time, they offer a force equal. These constraints are offering a force as reactions. Okay, so what is the difference between action force and reaction force? If you have, say for example, a situation like this, how do you find the force which is an active force or action force and the forces which are reactions? Here you know that weight, by intuition or by practice you can say that weight is your action force. Why can't this be an action force and these two are reactions?
Because
yeah?
Only weight is there, the other two forces come.
I didn't get it.
Only weight is there, the other two forces.
Okay, if the weight is there, other two forces will be there. If it is a weightless ball, the other two forces are going to be zero. You are right. So what I can say is, instead of going to that extreme, you can say that if I change that action force by magnitude or direction. For example, if I W, I change it, other two forces are going to be changed. But if I change the R, this is not going to change, isn't it? So if you have the action force and reaction forces, action forces, if I change them, as he said, the limiting case, you remove it completely, then you see the other forces will be there or not. Okay? So that can, by that you can distinguish whether the such force is an action force or a reaction force. Okay. Now you have any doubt? We have discussed about constraints, what kind of reactions can come from a constraints. Now we go to the next very important topic in statics, that is called free body diagram. In any problem in statics, the first step is to draw a correct free body diagram. Okay? Once you have drawn the free body diagram correctly, then the solving the problem is going to be quite easy. If you do a mistake there, it's very unlikely that you will solve the problem properly. Okay? Now what is a free body diagram? It is a diagram. It is a diagram in which the constraints are removed. Okay? So if I say this, I want to draw the free body diagram of the ball, you have to remove the constraint. What is the constraint here? The string. String should not be there. Can I do just like that? So in this problem, what are the constraints? The string and the wall. I have to remove the constraints. Free body diagram won't show the constraints. Constraints are removed. Not just like that. The constraints are removed after incorporating the appropriate reactions from the constraints. Okay? If this is the ball and the string is a constraint, for drawing the free body diagram, I remove the constraint, that is the string, not just like that, but I have to incorporate the reaction force given by the constraint, that is the string. Okay, is that the free body diagram? It means that free body diagram in general, so all the constraints are removed, only the body is shown. The body under consideration, the body that you want to test its equilibrium, that is called a free body diagram. Okay, that is freed from the constraints, but that is not the complete definition. First thing is free body diagram, the constraints are removed by appropriate reactions. Okay, so free body diagram is a diagram where the constraints are removed by appropriate reactions. Appropriate is important because if it is a frictionless wall, I will have a reaction normal to it. If there is a friction, it has to be at an inclined way. I have to carefully think and then put an appropriate reaction, not just like that reaction here. I have to consider the constraint, the nature of the constraint, and find out what is the appropriate reaction, then I have to put it. Now it is not the only thing. I have to show the action forces also. Don't say that I have a free body diagram wherein the constraint is removed, the string is removed by reaction. This is not a free body diagram. Free body diagram should include the action forces also. That means it should include all the forces which are acting on the body. But is it the definition is over? More or less it is over. But one of the other things people violate is that it should reflect the shape. So it should conserve, or I would say represent the shape. It should represent the shape of the object that you are talking about. If I say I have the ball which is hanging using the string, I want to draw the free body diagram of it. So I should not say consider this as a ball, this is the reaction, this is W. Consider this as a ball. No, it should not be. It should be reflecting, or it should represent the shape, general shape. For example, in senior classes, if I ask them to draw the free body diagram of a chair, considering that as a two-dimensional object chair, they will just put something like this and say consider this as a chair. No, it should represent the shape. Okay, so at least you should say that looking from one side it has two legs. It should conserve it should be reflecting the shape of it, what you are dealing with, the body that you are dealing with. Don't say any these things, the arbitrary shape, and say that this is a free body diagram. Definitely not. So there will be cases where the problem dealing with a human being, it should represent the free body diagram should represent that it is a human being. Don't say that this is a human being. No, at least you don't have to be an artistic thing. At least you say that this some representative shape, that what you are dealing with, whether you are dealing with an object like chair or a human being or a truck or an aircraft. So those shapes must be there. Okay, it should not have constraints. The constraints are removed by the appropriate reactions. Not only reaction, the action forces also include. That means the entire system of forces acting on that is truly represented. Then it should also reflect, represent the shape of it. That's called a free body diagram. Okay, so it's a very important first step in solving problems in mechanics. You have any doubt? Okay, with this we close this class.